Right, so this lecture is going to be a short, sort of a impromptu lecture that I got while I was watching a movie. So this movie was Call Me by Your Name, and it's a gay romance movie. I'm sure you guys already know this movie, I swear. And there's a very interesting sort of philosophy behind the notion that Elio and Oliver called each other by the other's name. So Oliver would call Elio Oliver, and Elio would call Oliver Elio. So they call their partner with their name. So yeah, and that got me thinking. Okay, so if they sort of have this identification of each other in this manner, this sort of sounds like an equivalence relation. Okay? So, an equivalence relation. Of course, they are inside a relationship, but we are now talking about a very important mathy thing, and it has its roots in everything from topology to group theory to even linear algebra. Okay? So, an equivalence relation. So, you notice that if Elio is essentially what Elio calls Oliver, oh, Oliver, then it must hold that the reverse is true. Oliver is equivalent to Elio. And so this demonstrates what is called the reflexivity um, of an equivalence relation. That is, if I have two mathematical objects A and B, an equivalence relation on them, let's do the formal definition. Okay. So definition. Two objects. Could be anything. It could be maps. It could be sets. It could be spaces. Given two objects, A and B. An equivalence relation is a um, is a binary operator, which we denote via tilde. Now there are many different equivalence relations. One example of equivalence relation is a homotopy between two curves or between two topological spaces, and of course homeomorphism is an equivalence relation. Mainly because if one space is homomorphic to another, then the converse is true, that other space is homomorphic to the first space. And likewise, if I have two curves that we say are homotopic, if one is homotopic to the other, then the other is homotopic to the first one. So it makes sense. So it's a binary operator that takes the set AB across itself, mainly just the pair AB, and takes it to the set A equivalence B or B equivalence A. Okay, such that tilde is reflexive. One, you can argue that tilde here could be commutative in the sense of the operator, like addition being commutative, and then thus the group we equip it with becomes an abelian group. But what I want to emphasize here is that I can switch the members around and it would be the same. Okay. And transitive. So now we're not talking about just AB when we're saying transitive, but now we're talking about a set A. So a set A tilde B such that A and B are inside A. So for any AB, so all sets of equivalence relations. And in fact, this constitutes what we call an equivalence class, which we will discuss later. Okay, so equivalence relations, binary operator is reflexive and transitive. What do I mean by transitive? So if I have three elements A, B, and C, A, then it must hold that if A is equivalent to B and B is equivalent to C, it's A is equivalent to C. So the notion of an equivalence relation ranges over a lot of concepts. It's a general concept, okay? And we have encountered this a lot of times before, especially when talking about modular arithmetic, finding quotient groups, even quotient spaces. In the case of the quotient group, the equivalence relation sort of makes elements of the group equivalent, given that their difference is divisible by n, which we mod the group out by. And in topology, we identify 2 points, right? It depends on how you want to define the quotient topology, but if you define it over a single space, like say a disk, and you take its quotient space, obviously then we identify 2 points if and only if. This equivalence relation is identification in topology, right? And we identify 2 points if and only if they lie on the boundary. So if they lie on S1, which encompass the disk. And so equivalence relation in topology is identification. So we make 2 points essentially the same exact point in our abstract space or abstract world. So that's the definition of an equivalence relation. And of course, also in foundations, we use this in foundations when we were trying to construct the integers and especially the rationals. Okay. So we use this notion then. So let's visit. So we're now going beyond just the movie and now diving into the actual notion of an equivalence relation. So now let's think about, okay, so if I have a set and its elements, what exactly are the set of all possible equivalence relations I can have on that set, right? I can have on elements in that set. That's called equivalence class. So definition. An equivalence class is the set of all equivalence relations. Set of all equivalence relations defined on the set. So the reason why we want to define an equivalence relation on a set, we cannot just say, okay, A and B are identified, because that's not well defined. So you recall in a previous lecture that a certain operator or a map is not, or a function, homeomorphism, homotopy maybe, these are not well defined if we don't exactly define what they do. So if you end up with people asking questions about the very characteristic of a mathematical object that you sort of just told them about, it's not well defined because there's ambiguity over there, and we don't want that. So we want to make sure that our object is distinct from any other objects, and that it isn't just sort of a rebranding of a pre-existing mathematical object. So that's why we want our equivalence class or our equivalence relation to be well defined over the set. So you'll notice that if in an example a while ago in topology, so points A, B are only identified if and only if A and B lie inside the boundary of B2. And this is the equivalence relation we define over over the quotient space of the disk. And you notice that there's this crucial this crucial string over here, which is if and only if AB inside the boundary of B2, which is S1. Okay, so very important that we define what exactly are the conditions for 2 points to be identified, or to be put inside this equivalence relation, or exactly what elements we can put into it. So it dictates our range. But not only that, but it makes it well defined. Okay, and of course, we can not only can it be like a membership type of thing, but like, or an inclusion, or but it could also be a formula, right? If, for example, let's say that I want to identify stuff on a sphere, so that means I would have to say that they satisfy x squared plus y squared equals the radius squared of the circle. If it's the unit circle, just one. So if I want to identify points in the circle, right? If I want to identify the points in the circle and collapse them onto a point, I want to contract the circle onto a point, then I would say that I will identify points if and only if points x and y, if and only if they satisfy that equation. So this is an example for retract. So x identified with y, if and only if x squared plus y squared equals 1. So x and y here lie in the unit circle in any space that you want. Maybe it could be C or R2. But the point is, this sort of equivalence relation shrinks the circle down onto a point, a singular point. It could be anywhere inside that space that you put your circle into. But the point is, the point is they all get to 1 point, and that's the point of the what I'm saying here, that I define what exactly x and y must satisfy in order for them to be identified or put inside the equivalence relation. Okay. So if I have a set x, or if I have an element x, I suppose we denote an equivalence class, right, of any element x in a set to be this bracket x. And you would have seen this already in algebraic femboid theory. I used this when I was defining the quotient group. And in fact, there are certain homotopies that are equivalence relations, or that can form equivalence relations. And in fact, a homotopy is, as I said a while ago, an equivalence relation between two curves embedded in a space, or in a space embedded into another space, of course. It's a general definition, not just curves. But either way, when we have our equivalence class, we essentially say that, oh, okay, it's a bunch of homotopic curves that close in on a hole in our space, and so it detects the hole, because we can make more curves that shrinks further into the hole, because there's a hole there and it's not defined, or that space is that's a hole is not defined, and we cannot shrink our curves further or our loops further. So this is the set of all equivalence classes of elements x in our set x. So we can also denote it like this, such that x is an x. And I suppose you can also define what exactly the equivalence relation is here, but I will assume it is already predefined in the definition of what exactly your equivalence relation is. So this is a set of all equivalence classes. And in fact, another example of this, aside homotopy, is the new numbers that we get from modding out a number from the integers, or assembly from assembly. So if I have, say, f, I have a subset of f such that, well, a is equal to the first, let's see, 10 femboys. Then a mod f, say 5, the fifth femboy. gives me something that's like this. F0 up until F4. But the thing is, F0 up to F4 are not precisely elements of A here. They are not just regular femboids here. They are in fact symbols or notation, symbols for equivalence classes of any element, so containing all elements that are essentially the same, because when we subtract those femboids, we can divide that by our fifth femboid, right? So most mathematicians, you'll notice, will denote these guys with a dash on top. That's because these are fundamentally different from the original femboids in our set A. Because each Fi bar is equal to an equivalence class of Fi under this equivalence relation. And the equivalence relation is that it takes in two femboids, Fa and Fb, and they are identified, and takes them to Fa identified with Fb if and only if f of A minus f of B is divisible by F(n), which we mod out the entire thing, which in this case is F5. So that's one example of an equivalence relation in our theories. So yeah, I know this is a very short lecture, I know it's just 16 minutes, but I wanted to discuss this thing, and it's just a spur of the moment type of lecture. So hope you guys enjoy this. And it was an impromptu lecture, it's just off the top of my head. And frankly, this thing happens to me whenever I watch a movie or something like that, that a sudden idea pops into my head and I wanted to lecture about it. So really cool concept that's very important throughout mathematics, and especially our courses. And so that's a good place to stop.